copy is find out the distance between the point and the plane. If there's a point above the plane in 2D, then there's a formula to estimate the distance between the plane and point. So we have to first set up the normal vector on the plane, and the reference point on the plane to arbitrary direction can be defined by the vector. So the way to define the distance from that point to the reference point could be given by the dot product and the normal vector. Let me show you how to define the distance between the point and the two-dimensional plane. So let's assume there's a two-dimensional surface, and basically we set up the direction with the normal vector on the surface, so that there's a point on the surface of the plane that is point P, which is the reference point, and that the point above the surface is labeled with a Q. So what we need to do is find out the distance between Q and this surface A, the plane. This is normal vector, and now the directional vector from reference point P to the point of interest, the Q, could be defined by PQ, that is vector P and Q. And the best way to define the distance between the Q and the plane A is to project the Q onto the plane A and normal vector N. So let's split that vector PQ onto the plane A and normal vector N. So if you project that, it should be like this. So that is perpendicular. That vertical line out of this Q onto the plane A is perpendicular to the plane A. Now also you extend the line horizontally onto the normal vector N. So the distance D, now this projected vector onto the N from the back vector PQ could be defined by project N of point PQ. So distance D from Q to onto the point A, B, is the magnitude, amplitude or magnitude of this projected vector PQ onto normal vector. So that could be also expressed with the magnitude PQ plus dot product normal vector N divided by the magnitude of normal vector. That is definition of the distance D of point of interest to the plane of area A. So to find the point in the plane given by the ax plus by plus cg plus d equals 0, then from the equation ax plus d equals 0. So you can conclude that the point minus d over a 0, 0 lies in the plane. So let me change the color. So to find a point in the plane given by ax plus by plus cg plus d equals 0, that is plane A. here's A should not be equal 0, and the Y, then you should just let Y equal 0 and Z equal 0. Then from the equation, this equation change to the AX plus B equals 0. Then you can conclude that the point, so that's X should be that minus B over A. And the point on the plane should be the X minus B over A, 0 and 0. That point should be on the plane A. So that could be the point can be used as reference to justify the distance too. So let me just go with this definition with the example problem. So let's find the distance between Q1, 5 minus 4, and plane A, 3x minus B, plane Y plus 2z equal to 6. Here, normal vector, as you know, this is A, this is minus 1 is B, and C equals 2, and D is minus 2. From that, normal vector, based on its definition, 3 minus 1, 2, but this is A, B, C. So now let Y equals 0 and Z equals 0. Then that should be 3x equals 6, so x is 2. So the point on that plane A should be 2, 0, 0. Now the PQ from that should be 1 minus 2, 5 minus 0, and minus 4 minus 0. So that is minus 1, minus 5, minus 4. So use this point, you can estimate the distance between the point and the plane. Based on the definition, it's PQ, absolute value of dot product between PQ and normal vector n, divided by magnitude of normal vector. So that should be minus 1, 5, that should be 5 actually, 5 minus 4, dot product 3, minus 1, 2, divided by normal vector is, the magnitude of normal vector is 3 squared plus minus 1 squared plus 2 squared. So that is square root of 14. So from that is that should be minus absolute value of minus 5 minus 8 divided by square root of 14. So that is 16 over square root of 14. That is distance between this Q and the plane A.
So, Luke, do you think, oh, hold on. So do you think you understand how to use that formula to estimate the distance between the single point and the two-dimensional plane in the case that those two formula are provided?
Yeah.
So basically, the one you see that D equals the absolute value of projected vector PQ on the normal vector n is the distance between the Q and the plane A. Okay, so you gotta just, the one you see, this one is the question you have memorized to is estimate the distance between the two objects in three-dimensional space, Q and the plane A. Okay. Any questions?
No.
Okay, then we're gonna move on to the chapter 11. That's the end of the chapter 10. So we're gonna switch gear to the limit and the introduction to the calculus, which is chapter 11. You will have scheduled to actually learn about these topics in near future in your school classroom curriculum. So let me pull up another video. So that's about 1 hour, probably 15-minute video, which giving you some overview of the limit and introduction to the calculus. So let me open it up. Okay.
Chapter 11, Limit and Introduction to Calculus. So Chapter 11 is dedicated to introduce the basic concept of the limits and calculus, including derivative and integral. So especially first subchapter of Chapter 11 is just showing the basic idea of how limit works for defining the extreme case of the numbers. So we're going to start with the definition of a limit as the first part of the chapter 11.1, and just get used to that idea by solving some example problems. So chapter 11.1 is concept of limit. As first part of this chapter 11.1, we have to just check how the limit is defined in terms of the basic function describing that the x, y, z coordinates. So let me just write it down. The definition of limit. So normally, limit is defined with this description. If function fx becomes arbitrarily close to a unique number L as x approaches C from either side, the limit of function fx as x approaches C is L. So this could be actually expressed with the symbol of a limit. So if you use that basic symbol of limit, that should be limit x approaches C, fx is L. So this is easy way to define the concept of the limit with the constant values L. So let's take a look at the basic concept of limit with the example problems. So let's just bring up some example function. fx now is 3x minus 2. Then now if limit case of x approaches to 2 of this function fx, then there should be a limit x approaches 2, 3x minus 2. So now if the number of x goes to getting close to number 2, you will see how that fx, the limit case of fx actually becomes kind of what number. So now let's set up the table. I'm going to list x values from the lowest number to the highest number. I'm just like randomly pick up the numbers, but with some range of scale. So let's just start with 1.9 in x, and that's move to 1.99 and 1.999 and 2, then gradually getting bigger and bigger. That's 2.001, 2.001, and 2.1. So with that numbers, fx becomes, for example, 1.9 of x. That makes this fx is 3.7. 1.99 makes this fx 3.97. 1.999 of x makes this fx 3.997. And 2, if you plug that into the fx, then that becomes 4. And 2.001 make fx 4.003. 2.01 make fx 4.03. 2.1 makes fx is 4.3. So you can see the trade-off of the fx in terms of the x value. So as fx becomes bigger and bigger and approach the number 2, and you can see fx becomes bigger and bigger and getting close to number 4. Once you pass through the number 2 of x value, then fx becomes bigger, and the difference between the jth number and number 2 becomes bigger and bigger too. So depending on the where you're looking at, which direction you're looking at, as x approach the number 2, then fx also approaches number 4 from minus negative direction and positive direction. So x value to get into the number 2 is fx becomes closer to the number 4. So as you can see, it set up with the limit case with the x with the number 2, then fx becomes number 4 based on this given function. So in some cases, limit doesn't work. So we're going to take a look at the case that the limit is failed to exist. So for example, let's take a look at the function with absolute value. So this is example, limit of x approaches 0 for absolute x of x. So if you plot this x, there's 2 different numbers possibly existing. If x becomes large, the positive number, then absolute x of x equals x over x, which is 1. But if smaller than 0, there's a negative value, then absolute value x of x becomes minus x over x, so that is minus 1. So if you plot this one, then that should be like this. This is x, this is y, this is fx. So it comes from positive x to 0, then this fx becomes plus 1. If it comes from negative values of x to 0, then that is minus 1. So this area, these numbers at x equals 0 is discontinued. So in this case, that you'd not be able to actually define limit case because depending on which direction you are looking at, that function absolute x over x becomes plus positive 1 or negative 1. So there's no way to define this value of limit case. Another example might be possibly. Let me show you another example. Let's take a look at the inverse power function of x. So basically, if the function f(x) is proportional to the 1 of x squared, then if you plot that, then the value of f(x) diverges when x equals 0. You see that from this graph. So if you take limit case of x goes to 0, or the fx, the 1 over x squared, then and you can see the x of x goes to infinity. So that doesn't also, this limit of function fx does not have a solution. All right. Let's take a look at some properties of limits. Okay. So let me clean up this page. Okay, so let's take a look at some properties of limits. I'll just take it off first. So, I need to change the color of pen first. So, the property of the limits. So basically, if x goes to c in the limit with the function fx, then the value of that limit case is same as the fx with x is c. So if you plug the c into in this function fx, replace x with the c, then that is the solution of this limit of fx in case the x goes to c. So let me show you the basic limit case, basic property of limit. Number 1, if x limit b for x goes to c, then that is just same as c. So if you have constant value inside the limit, then that doesn't change property of limit. So it should be same as just constant value of b. So number 2, limit of x for x goes to c, then that is the limit x for x goes to c, then the solution of that case is c. Just all you need is plug the c into the x. Number 3, you have power function, polynomial function inside of this limit, then that should be same as c to the power of n. So basically all you need is just replace x with a c if x goes to a c. Number 4, limit of x to the power of 1 of n. In case x goes to c, then same thing, need to plug c into the x function of fx. So that has the answer and the solution of n square root of c. Let's take a look at the property of the limit again. So properties of limit. So the limit of x is equal L in case x goes to c, and limit function gx for x goes to c.
So Luke, I'm gonna give you time to solve the example problems yourself. So pay attention to the what is being shown in this whiteboard. You have to use some of this formula to solve the example problems. So, well, all right, we'll continue.
Equals k. Then number 1, scalar multiple. If the function fx is multiplied by constant scalar number b in the limit, like this, and that goes to c, then that should be just b times l, because b can that should be b actually, because b can be out of this limit, so that could be first taken out of this bracket. So if you take a b out of it, then that's just same as b times limit of function fx for c goes to x goes to c. So this one is l, so that should be b times l. Next, sum or difference. Number 2, sum or difference. If the function inside the limit with the fx and gx, then this limit could be applied to the fx and gx separately. So limit can go into the first term and the second term. So that could be expressed with the limit function fx, x goes to c plus minus limit of gx, and x goes to c. Here, limit fx is L, and this limit gx is k. So that could be L plus minus k. Okay, and the product, number 3, product. The inside of the limit consists of fx and gx and their multiplication or their product, like this. Fx and gx, x goes to c, then just like sum or difference case, that limit can be split into the fx and gx separately. So you can actually express with the limit of fx times the limit of gx with c. So this one is L, this one is K, so that should be L times K. Okay, that is product rule. And number 4, quotient rule. Same thing, same thing like the product rule. So that limit fx over gx. So that limit can be applied to numerator and denominator separately. So this one could be limit fx x goes to c, and the limit gx x goes to c. So the numerator and denominator could be expressed with L and K. So that should be L over K. Here K should not be same as 0. Otherwise, if K goes to 0 or K is 0, then that makes this value goes infinity. Number 5, our rule. So that is limit fx to the power of n or x goes to c, then that should be that limit can be plugged into the as power. So that is same as limit fx x goes to c to the power of n. So inside of this bracket is same as L. So the result is L to the power of n. That's the properties of the limits, and we gotta just move on to the next properties of the limit with the polynomial and the rational functions. Let's take a look at it, and we'll just find just an example to use that properties to solve the problem.
Okay, look, before moving on to the next topic, do you catch any concept of this definition of the limit? Do you know how it works? Why we need to use the limit? What is that for? Do you have any ideas?
No.
Okay, then let me give you an example before moving to the next one. So hold on a second. Let me pull up the PowerPoint slide to explain the ideas. So the reason to use limit symbol for expressing that the mathematical quantity. So let me give you one good example. So if you have some numbers and you have to actually just get into stay very close to some specific number, or you're far away from that, then you can't just use that the really small quantity of mathematical numbers to express that the quantity of that numbers. So for example, now let me give you the example. So hold on. Now let's just give you some examples. Now we have 1, right? That is numerator, and now you divide by 1. What is this?
1.
Okay. Now you numerator is just the same as 1, but it's divided by 0.1. What is that? 1 divided by 0.1.
10,
How much?
10,
Okay, 10. Now, numerator is the same, but you just change the denominator is 0.01. What is that?
100,
Okay, 100. What about the 1 divided by 0.001?
1000,
Okay. So what about the 1 divided by 10 to 1 minus 6? 10 to the power minus 6.
1 million,
1 million, right? So basically, now numerator, they're same, doesn't change. But look at the denominator. The number becomes smaller, 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 smaller. So that basically the denominator, the size scale of the denominator goes to where? So let's just symbolize that the numerator is y and denominator is x. Y is just 1, stay as a 1. But x now goes to where?
0,
Yeah, you see that the kind of trend? X goes to 0. So in case you have y over x and x goes to 0, then what number that if you think of the y over x is c, then where c goes to? So this take a look at the c. This is c, and now it's that if you put the 1 in denominator, it was 1. Now if you put the 0.1, c becomes 10. 0.01 of x make this c becomes 100. Now 0.001 of x makes c is 1000. Now change to the 1 million if we put the 10 to the minus 6 in x. If you keep on going, then as x goes to 0 and c goes to where?
infinity,
Yeah, it goes infinity. So this whole scenario could be symbolized by the simple notation of a limit. So limit, I just express whole thing, whole dynamics of evolution of numbers of x from 1 all the way to the, 0, right? I have made the x value is really small, teeny tiny. So x goes to 0, and the y of x of function, which is fx, goes to infinity. So that is like some of the okay, right there.
Okay. Next one, you want to actually check the limit of polynomial and rational functions. So, next one, hold on. Okay, so here, what you need is just replace fx with the polynomial function px and find out how that px expressed in case that x goes to some finite number c. And also we'll find out how rational functions with the polynomial function at px and the gx can be expressed in case that x goes to some finite number c. So if fx is function of polynomial function like this, the limit of that kind of function, in case the x goes to c, then you just need to replace x with a c. And number two, if there's a rational function inside the limit, which is expressed with the px and gx. Here, g x is c is not equal value. Because otherwise, gx becomes zero, then make this rx function goes to infinity. So there's no solution. And now, if you find that the value of rx, in the case x goes to c, then that should be same as rx, but with the x is c. So you replace x with c, then the limit of that rx should be rc. Now rx is the px over gx, so if fully expressed, then x should be replaced with c. Same thing for denominator, x should be replaced with a c. So that should be fc over gc. That is genetic solution for rational functions. So let's take a look at example problem to find out how those rules work, like in case that fx function is either rational function or polynomial function. So example number 10. We want to find out the limit of fx, which is x squared plus x minus 6, in case the x goes to minus 1.
So, Luke, can you solve this problem? Can you find the value of limit of x squared plus x minus 6 as x goes to minus 1? Hold on a second. Let me check if there's more.
So you plug that into.
Okay, go on.
-6.
How much is it?
-6.
Yes.
The formula that should be minus 1 squared plus minus 1 minus 6. So that should be 1 plus 1. I'm sorry, that's actually 1 minus 1 minus 6. So that would need the minus 6. And now we want to actually look at limit case of rational function. So the function is defined by x cubed plus x minus 6 over x plus 3. So the case x goes to minus 1.
Can you solve this problem too?
-2.
Maybe 2. Let's see if that is the answer. Correct answer.
So now you plug -1 into this formula, then that should be -1 square plus -1 minus 6 divided by x plus 3. Here x is -1, right? So that is -1 square plus -1 minus 6 and -1 plus 3 over. So this one, as I said, x1 minus 1 square plus -1 equals 0. And now the denominator is 2, and the numerator is -6. So the answer is -3. For example number 10. So let's move on. Next topic in this chapter is to set up to find that some techniques for evaluating the limits. So we will go through some basic technique to find out the value out of the limit for some functions. So the first technique is dividing out technique. So that is number 1 technique to evaluate the limits in some condition. So chapter 11.2 techniques. For evaluating limit. The first technique is dividing out our technique. So let's just solve example number 1 to find out how to use the dividing out technique. So example number 1. Example problem number 1. So that is, there is a function, rational function, the x plus x minus 6 over x plus 3. And we want to find the value out of that function in case the x goes to number 3. So that is limit of x squared plus x minus 6 over x plus 3, or the x goes to -3. So now we're going to do some rearrangement.
So Luke, can you guess what would be the answer for this question? You can try to solve it yourself if you can. Surely I will show you the answer right away.
No solution.
I'm sorry, what?
No solution.
No solution? That's your answer? No solution is your answer, or you want to solve it again?
0 over 0.
0. How much? I couldn't catch you.
0 over 0.
0 over 0? Okay, Luke, just answer. I can't hear you.
Zero over zero.
Okay. There's some way to actually solve this problem because if you plug the -3 in denominator, that becomes 0, right? And that will be the -6 divided by -3. So that make this answer diverse, that there's no solution. But actually, that's not the way to solve this problem. You have to divide the numerator with a denominator first, and then plug the -3 into this function. So numerator. So if you just reset like a numerator with the variable separation, then that should be x plus 3 times x minus 3. And there's same type of term in the denominator too. So x plus 3 could be canceled out of the numerator and denominator because that coexists in those two, numerator and denominator. So that could be simplified by the equal and the same term and canceled out of the numerator and denominator. So that should be limit x minus 2 in case the x goes to -3. So in that case, you just need to plug -3 into the x. Let's see, -3 minus 2 should be -5. Okay. Also, let's take a look at the example number 2. Becomes more to become more familiar with this technique, dividing our technique. So the number 2 is to find out the value of the function f x, which is x minus 1 over x cubed minus x2 x squared plus x minus 1 for the case x goes to 1. So we have to separate this function in numerator, the denominator. So that case, the limit x goes to 1, then x minus 1 over x minus 1 times x squared plus 1. So if you expand the denominator, then x minus 1 times x squared plus 1 must be equal to the x cubed minus x squared plus x minus 1. So there's a common term in numerator and denominator, so you can cancel them out. X minus 1 from those two positions, so that should be x the case of the main term in numerator and denominator, so that the numerator becomes 1 after canceling out an x minus 1 term, and denominator should be x squared plus 1. And x now goes to the 1 or approach the 1. We only need to plug the 1 into this function, so that should be 1 over 1 squared plus 1, which is 1 over 2. That is answer for this problem. So next technique is rationalizing technique to solve the limit case of the function. So still, we need to take a look at the example problem to find out how this rationalizing technique works. So the example number 3 is we want to find out the function f(x) square root x plus 1 minus 1 over x in case the x goes to 0. That is square root x plus 1 minus 1 in denominator, and numerator is
the numerator is square root x plus 1 minus 1, and denominator is x. So in this case, we have to actually just convert these two terms out of numerator and denominator with the additional multiplication. So we kind of like rationalize this two numerator and denominator terms, so that help to actually add the x value into the given modified formula or function. So now we want to actually multiply convolution actually term to numerator and denominator of the x square root x plus 1 minus 1. So if you do that, that should be at limit case that so limit x square root x plus 1 minus 1 for x times square root x plus 1 plus 1 to numerator, same term should be multiplied to denominators. So the x square root x plus 1 should be multiplied to the original function, and we are find out that value of those modified function in case the x goes to 0. So you continue, multiply this additional numerator and denominator term, sort of like rationalizing this function by multiplication of the same convolution term in the numerator and denominator, then that should be limit x goes to 0. And numerator is the x square root of x plus 1 square minus 1 square. Denominator is x times square root x plus 1 plus 1. So this first term in numerator is same as x plus 1. And you have second term but with the minus sign. So 1 can be cancelled out of the numerator. Only leave x term. So that should be limit x goes to 0 and x over x times square root x plus 1 plus 1. So the x, the numerator, both numerator and denominator has the common term x. So that could be cancelled out with each other. That could be cancelled out from numerator and denominator. So in that case, the remaining term is 1 of square root x plus 1 plus 1. And we want to find the value of that function in case that the x goes to 0. We plug that number into this formula, then that should be 1 over square root 1 plus 1 plus 1. Now this first term equals 1. So that should be 1 over 2.
Okay, Luke, do you have any idea how this dividing technique works? The way you find out the value of the function in with the limit?
Yeah.
Okay, so yeah, that's probably end up for today's session. I'll gonna just upload this video file in your account in my website, and you feel free to take a look at it when you need the review of today's session. And I heard from your mom today is your last session. You said you do not need any more tutoring, right? As far as I understood correctly. So ask your mom. I mean, talk to your mom that today's session is complete, and I'm gonna just maybe just wrap up your tutoring as of today. Does it make sense?
Yeah.
Okay. All right. Then good luck with your semester. Hopefully you have the good outcome from the this subject in this semester, and hopefully you better outcome at the end of the semester too. All right. I'll see you sometime in the future. Good luck with you.